Hello everyone. So in this video I will be covering some of the most popular machine learning algorithms that are in existence today. So the machine learning algorithms that I will be covering in this video are linear regression, logistic regression, decision tree, random forest, support vector machines. So these five I will be covering in this particular video, and in the next video I will be covering k nearest neighbors, also known as KNN, naive bayes, gradient boosting, neural networks, and k-means clustering. So let's get started with linear regression. So linear regression is a supervised learning algorithm that is used for continuous target variable prediction. So it is trying to predict a continuous number, and that is the target. So just imagine some kind of number, a continuous number. So it could be the price of certain item, or a value or numbers. So it's not a classification. It's not like a yes or no or a binary problem or a multi-class. So it is a continuous number that we are trying to predict. It models a relationship between the independent variables and the dependent variable by fitting a linear equation to the observed data. In simple linear regression, there is only one independent variable and the equation takes the form of. So this is the equation for a single, like when we have only one feature. For example, if y is what we are trying to predict, so y is the target, for example, house price. So this is the dependent variable we call dependent variable, and this is called as y, and it depends on a constant like intercept. B0 is called as intercept, plus this x is independent variable. So this is dependent, this is independent, and for example, this x could be something like the total area of the house. So total area of the house multiplied by some coefficient, some parameter, plus some base value. This is called as intercept, and that will be giving a target price of the house. So this is the most simplest form, but there will be plus other features as well. So this x1 is one of the features. So this is the simplest form, just to make it make you understand what is a linear regression. So where y is the dependent variable, x is the independent variable, and b0 is the y intercept, and b1 is called the slope of the line. In multiple linear regression, there are more than one independent variable, and the equation takes the form of. So in real world, it's always like there'll be huge number of features. It could be huge or multiple. So this, as I mentioned, x1 could be like total area of the house plus some multiplied by some coefficient plus, and then x2 could be something else. For example, number of rooms, then longitude, latitude. It could be some other categorical parameter, like is it in an urban area, rural area, and whether it's a single like there, if there's how many like floors are there. So all these features are combined together and multiplied by some weight, some coefficient, and there's some base value which is called as the intercept. Then finally that will give the target house price. So the goal is to find the best coefficients. So this is what we are trying to learn, b0, b1, b2, and all the way to bn, such that the line fits the data points as best as possible. This is usually done by minimizing the sum of squared residuals between the observed values and the predicted values. A graphical representation of a linear regression model is shown in the scatter plot next, where the line represents the best fit of the observed data points. So our model, so this is our training data, all the blue dots. So these are the actual data that we have collected. So based on that, so this is just in the real world, it will be like multiple linear regression. So there will be like x1, x2, x3, but just to make it visualize. So there will be, let's say, it's only the number, the total area of the house. So x is the total area of the house, x, and y is the predicted price, for example. So you can just think like some value like 2.5 into 100,000, like 2.5k, 300,000, 3.5. So this is the data which we have collected, and the machine learning linear regression goal is to create this particular line which best fit all the data points, and it has to best fit because the error should be the loss or the error should be as minimal as possible. So this line fits the best. But if there is a line, for example, going from here to here, the error will be very high. Or if the line goes something like this, if it goes something like this, it would be very high. So this line best fit. And in case if you throw a new unseen test data, it can predict by some very good reliable probability that what will be the predicted house price. So next I will be covering logistic regression. Logistic regression is a statistical method for analyzing a data set in which there are one or more independent variables that determine an outcome. It is used for binary classification problem. So this is slightly different. So this is used for classification problem where the goal is to predict one of two possible outcomes. For example, yes or no, pass or fail, 1 or 0. In logistic regression, a logistic function is used to model the probability of positive classes. For example, yes, given the value of independent variables. So it's same as linear regression. You have like a model, but the y is usually yes or no. So prediction is either yes or no with some probability, like what is the probability of yes, what is the probability of no. So total combined probability is 100% or 1. So probability of for example, yes will be 75%, no will be 25%. So the equation looks something like this. So p probability of y, so this is probability, and the actual equation will be 1 divided by 1 plus exponential inverse. Same we have the b0, which is the intercept, plus feature. So in this, if there is only one feature, x1 multiplied by b1, which is the coefficient, a weight which is multiplied to the feature 1. So in case there is only one feature, but of course in real world there will be many other features which will be taken into consideration. So the equation is like this. It can be also written like this, and here. So if I just make it simplify, so this is same as this, and this is same as this, and so just remember this e exponential raised to some power and ex plus 1. So this will become more clear as I explained. So you will see the exponential and divided by, so the whole this value will be very close to 0, or it will be maximum 1. So this will so for example in this table, so e1 or e's value is 2.71828. It's called a Euler's number. The e1 or e is equal to 2.718, and e0 so e raised to power of 0 is 1. So if I put all these number right into this particular equation, e raised to power x, ex plus 1. So for e, this is the value, and for e0 it will be 0.5. So you will see when e raised to power of minus 5, the value is very close to 0, 0.006. Then it goes up 0.01, 0.04, 0.11, 0.2. Then it comes to 0.5, which is half. Then at e1, if I put these numbers, it will be 0.73, e2 0.88, 0.95, 0.982, 0.99. So no matter how much, even if e raised to power 100, it will just go to 0.99999. So it will be very close to 1. And if it is e raised to power of minus 100, it will be like 0.0000000. It will be very close to 0, but it will never be 0. So the range will always be starting from 0, reaching all the way to 1. So that is the range for this particular equation. So this is how the graph looks like. For example, x minus 3, so it will be like starting from 0.05. So when x is minus 3, y value is like very low, 0.050. Then it goes to 0.135368. Then at 0 it become at x equal to 0 it becomes like 1, and then it goes up, and at 3 it is 20.6. so even if at 4 it will just keep going up like this. And for this is the inverse. So when x is minus 3, and if it is e raised to power of minus x, the graph is like reverse. So this become more clear when we look at this particular equation. So this is how the equation looks like. So there's multiple like features, and and where P of y equal to 1 by x is the probability of y being equal to 1 given the values of the independent variables x. B0 is the y-intercept, and B1, B2 all the way up to Bn are the coefficients that represent the effect of each independent variable on the outcome. The coefficients are estimated from the data by maximizing the likelihood of the observed outcomes given the values of the independent variables. The predicted outcome is then a binary value, example yes or no, depending on whether the predicted probability is above or below a certain threshold, often 0.05. So this is mostly we just put 0.05. So if the probability of yes is, for example, 0.55, then it will be taken as yes. So this is the default threshold, and if the no is 0.45, it will be taken as no. So if from it will become more clear from this graph. So that's why the equation fits the line. The range, as I mentioned, it goes all the way up to 0, but never reaches 0. So it will be like 0. Then it goes up. Suddenly it goes up because it's an exponential function. Then it comes here. So so this is the equation. So it goes all the way to as close as possible to 1, but it never reaches, and there is a threshold. So if the threshold is 0.5, so basically it will tell what is the probability of probability of class 1. So for example, whether somebody has cancer or not. So if the answer is yes or no, so if all the data points here will be having very high probability, like 0.9, 0.8, so 0.9, 0.8, 0.7, 0.6 for example, and 0.999. so all these data points here are 100% sure, not 100%, like pretty much sure that this is the classification is yes. But from this point onwards, as we go down, it will be like probability of no is very high. So we just keep the default threshold is 0.5. So any data point which comes here, it will be regarded as no, or and any data point which comes above the threshold, it will be regarded as predicted as yes. And this is a feature, and this is the probability of class 1. So this data points, for example, class 0, these are the red ones, and this is the class, this blue crosses are the class 1. But it's also possible that some in the real world there will be very few which will be in class 0, but still they have. But that's why we are telling the probability of how much the model is sure that where the data points is falling into, and with what degree of certainty. So next is decision trees. A decision tree is a tree-like model used for decision making and prediction in machine learning. It is a type of supervised learning algorithm that is used for both classification and regression tasks. In a decision tree, the internal nodes represent decisions or tests on the value of the input features, and the leaves represent the outcomes or predictions. The path from the root to a leaf represents a series of decisions that lead to a specific outcome. Each internal node is associated with a feature of the input data, and the decision at that node splits the data into separate branches based on the values of the feature. For example, if the feature is color and the possible values are red, green and blue, the node would have 3 branches corresponding to each color value. The process of building a decision tree involves repeatedly splitting the data into subsets based on the values of the features until a stopping criterion is met. Common stopping criteria include a maximum tree depth, a minimum number of samples in a leaf, or a minimum reduction in impurity. Decision trees are popular in machine learning due to their interpretability, ease of use, and ability to handle both categorical and numerical data. They are often used as a building block for more complex models such as random forest and gradient boosting. However, decision trees are prone to overfitting, especially when the tree becomes very deep and may not always capture the complex relationships in the data. To overcome these limitations, various techniques such as pruning and ensembling are often used. So this is an example. For example, you have you start with top, like a decision node. and then you have a branch based, so it could be these are the alternatives, so yes, no, or it could be something else also. So there could be more than two branches coming out, and then you follow, if this branch is true, you go you go down that route, and if not, you go down the other branch, other alternative, and then you make a decision again, and then again. So if this part is you go take decision yes, then you make one more decision yes, and this decision is the last decision, then finally what will be the outcome. For example, if the question is whether it should be yes or no, so whether the final answer will be yes based on this or not. If this one is no, and then you ask again this one more question, and then this is the other final outcome. So just you go down a path depending on the all the features or the test. So these are the features or the test, and in this example we are just dealing with the binary classification, like 1 or 0, yes or no. So these are the the prediction. So decision tree the model will construct a decision tree based on the data. So it will go through all the data. For example, you have a table with multiple rows, and then you have a house price which you want to predict. So it will be number of rooms, the total area, and all those things, whether you should buy or not, some decision like that. So it will become more clear from this example. For example, should I accept some job offer? So for example, there's a model which a machine learning algorithm has model has created. For example, if salary is greater than $80K dollars, then yes. If commute is less than 5 kilometer, yes. And if it is a regular work hours, which is around 40 hours or less, around 40 we can say, then I should take this offer. So if not, no. If commute is less, so in this case, but if commute is more than 5, then no. But you ask yourself one more question, whether there is flexible work from home. If the answer is yes, you will take this offer. If answer is no, you should not take this offer. And same way, if salary is less than 80K, for example, no. So the not more than 80K. So but then you can ask stock options around 100K. So yes, you should take this offer. Otherwise, no. So this is how the model which using the decision tree algorithm would look at all the data and construct the leaves and come up with either yes or no, or a multi-class. It could be for example, there could be more than two labels, two labels that target labels that it's trying to predict. So next is random forest. Random forest is an ensemble learning method that combines the multiple decision trees to improve the stability and accuracy of the prediction. So this is built on top of decision tree. Basically, you have multiple decision trees, and that's why multiple decision trees make a forest. So it is called as random forest. It is used for both classification and regression problems. In a random forest, a large number of decision trees are trained on a randomly sampled subsets of the training data. The final prediction is made by combining the predictions of all the individual trees, typically by taking a majority vote in a classification problems and by averaging the outputs in a regression problems. Each tree in the forest is trained independently using a different subset of the data and a different subset of the features. This process helps to reduce overfitting and increases the diversity of the individual trees, leading to a more robust predictions. Random forests are widely used in machine learning due to their high accuracy and ability to handle large and complex data sets. They are also relatively easy to use and have relatively few hyperparameters to tune. However, they can be computationally expensive because we have multiple decision trees. That's why they become computationally expensive. They can be computationally expensive to train and may not be as interpretable as a single decision tree. To overcome the computational limitations, various techniques such as parallelization and online learning are often used. To increase the interpretability, feature importance measures and visualization methods can be used to understand the relationships between the features and the outcome. So this is how the random forest looks like. So whatever decision tree we have constructed, for example, should I accept this job offer? So same, all the features, all the tests we have put, for example, this was the original one, and then we just move around the decision node. For example, this is up one path, for example, green. So in this case, it has made like this. So it has just done all the different combinations, and it has constructed like few of those decision trees. So when it has to make a prediction, it will make sure that it will go through all the decision tree. So in some case, the answer, for example, for should I accept this offer will be yes, no, yes, no. So if, for example, there are 10 decision trees, so there will be yes, no, yes, no, yes, no, yes, no, and then finally, if there will be 10 outcomes. So for example, then there will be majority. So if 6 of them are yes, then final answer will be yes, and if more than 5, for example, if 6 or more is no, then our final answer will be no. So it has actually constructed 10 decision trees for the same set of data, and it will run through all the decision trees and give the final prediction. So next is support vector machine. A support vector machine is a powerful and widely used machine learning algorithm for classification and regression problems. It is based on the idea of finding a maximum margin hyperplane that separates the data into different classes or predicts a continuous output. The maximum margin hyperplane is a decision boundary that maximizes the margin between the closest data points of each class, known as support vectors. These support vectors define the decision boundary, and the distance between the hyperplane and the closest data points is called the margin. The goal of support vector machine is to find the hyperplane with the largest margin, which provides the best separation of the classes or the most accurate prediction. In the case of non-linearly separable data, support vector machine can transform the data into a highly dimensional space and find a linear separation in this space using a technique called kernel trick. This allows support vector machine to handle complex and non-linear relationships in the data. So I'll be just giving one example. This is a very famous iris dataset, and this has got like 4 features like sepal length and petal length. So petal is the long in this flower, right? So sepal is this part, this long path, and petal is something which is like shorter path. So here this one is petal. So we have the 4 attributes. We have sepal, length, and width. So length, so we have length and width, and then same for petal, length and width. Then this data set has got like 3 class to predict. Like there is iris setosa, iris versicolor, and iris virginica. So based on these 4 features, it will predict one of the classes. So this much, if we take this particular data set and feed in into for example support vector machine, it would give. So in this case I have shown a simpler, like only on petal width and petal length. So petal width and petal length. So these 3 classes are indicated by 3, like this red, and then this you can see there are yellow dots. So all this data set have been classified into another class, and then this green dots. So this is like, because we have 3 data sets, there's a hyperplane which segregates class A from class B to class C. And if you want to visualize this more into like 3D, so this is how it would look like. So you have class 1, class 2, and class 3, and all the 4 features you have, like data points you have constructed, and there will be like a plane, like a hyperplane, which will be separating the blues dots from these gray dots and then the red dots. So once this machine learning model, this support vector machine model is created, then if you throw in a new dot, then based on the distance from the like hyperplane we call, it will calculate to which class A, class B, or class C it should be predicted. Support vector machines are widely used in machine learning due to their ability to handle high dimensional and non-linearly separable data, their robustness to noise and outliers, and their ability to provide good generalization performance. However, they can be sensitive to the choice of hyperparameters such as the regularization parameter and the kernel type, and can be computationally expensive for large datasets. To overcome these limitations, various techniques such as cross-validation and model selection methods are often used. To improve interpretability, visualization methods and feature importance measures can be used to understand the relationships between the features and the outcome. And that's all. Thanks for watching.